Hello, everybody. My name is Maxim Gayachi.
And my name is Mark Yermolov.
We are security researcher at Positive Technologies. Today we are going to talk about powerful integrated logical analyzer for CPU and PCH, which called Visualization of Internal Signal Architecture, or just VISA. So we would like to remind you that the methods described here are risky and may damage or destroy your computer, hardware, and your brain. Also, we want to pay attention that we got Visa Unlock for market platforms through a vulnerability which we detected. And if you find any mistakes, please let us know. It's important disclaimer. It's main feedback from Intel on our presentation. It's our understanding of Intel technology. We have three big slice. So a public documented technologies like instruction set, like system management mode, or instruction extension like SSE, IS instruction, and many others. And particular documented technologies like ME, like bootguard, like MSR register and KPI, and many others. Some of them are available after NDA signing. And Intel internal technology and internal documentation, it's internal buses, it's internal devices like EOSF, sideband, fuses, DCI. And today we will look at technology allocated almost at the bottom, such as ODLA, EOSF, and of course VISA. So VISA is very powerful technology for researchers. You can get low-level access to CPU and chipsets signals. As a result, it allows to study speculative execution or out of orders, and to help you to reconstruct of internal architecture. First of all, we will look at how the analyzer connected to external interfaces, and the next we will consider VISA in the details. After that, we will give you some information about security. So we will discuss evolution of Intel debugging tools. It is necessary for us to understand how to interact with a subsystem. So until 2050 year, you need a special main board and a special socket for access to JTAG interface and for debugging Intel chips. But since for 15 years, all JTAG capabilities available through USB port. It means you can use simple DBC cable or special Intel CCR adapter like that for debugging your platform. So through this interface, engineer can check in DDR, can get access to DFX technology, and can debugging microcode and much more. So the second important part of this chain of debugging technology is the Trace Hub device. It's a device integrated into chipsets or SoC, and about it will talk my speaker Mark Yermolov. Thank you.
Thank you. Now about hardware tracing on Intel chips in general. At first, it must be noted that almost all modern CPUs or chipsets have hardware tracing capabilities in one or another embodiment, and Intel chips are not an exception. But for Intel hardware tracing facilities, it is obvious that they were unknown for most exterior researchers and engineers. However, they are very powerful and can be useful for any system-level developer, hardware engineer, security researcher. Moreover, these hardware tracing facilities affect a whole platform security in that way, so now every hardware or software security feature should be reviewed or designed having them in mind. Today we are talking about hardware tracing in modern system on chips and platform controllers hubs. Central processor units also have whose facilities, but they differ and can be considered as legacy. Anyway, the newest hardware tracing facilities are integrated in a special system-level unit called Intel Trace Hub. They consist from VISA, or Visualization of Internal Signals Architecture, ODLA, on-die logic analyzer, and SOCHAP, SOC, Chipset Hardware Architecture Performance Unit. They are completely controlled by Trace Hub MMIO register space and leverage all of its wide facilities, such as common trigger sequencer, trace data collectors, and various transports for trace data extraction. Intel Trace Hub is an Intel answer for need to collect all of the platform's trace data in one place. Its internal code name is NordPIC, and it collects data from hardware, software, and firmware sources. It is integrated in all modern SOCs and PCHs, starting from Apollo Lake Atom SOC and Sunrise Point chipset for Skylake-based platforms. In public, you can find one of the earliest developers' manual for Intel Trace Hub, where you can find the following scheme, depicting all of its internal components. Despite mentioning ODLA, VISA, and SOCHAP, there is a special unit called Global Trace Hub, collecting data from various trace sources and sending them to system memory, direct connect interface, and parallel trace port. Intel has developed a comprehensive software stack supporting the Trace Hub. Unfortunately, there is no any public documentation how to use the software. However, the software is provided as part of Intel Trace tool, which is a component of Intel System Studio. The software consists from two large libraries, Intel Trace Hub IP and Trace Decode Engine. Intel Trace Hub IP is intended to configure Trace Hub hardware for various trace sources and set up it to translate trace data via a number of hardware interfaces. Trace Decode Engine is a fabric of automatically selected decoders for binary data extracted from Trace Hub. Both libraries have configuration utilities exposing their functionality. Both libraries are configured using numerous XML files. We will show later the sample command lines for both libraries' utilities, which can be used to start and decode trace data from hardware signals.
Okay, so now we'll show you small
demo illustrating Trace Hub functionality for firmware tracing called Converged Security and Management Engine.
One moment. So,
Here we're using mentioned utilities, first for TraceHub IP and second for Trace Decode Engine.
We freeze the starting of ME core.
We instruct to reset ME core, so it traces the startup process.
You can see messages from ME.
And we use standard interface for system trace tools to use messages from management engine.
And so you can see the messages from ME, like from VFS module, from kernel, and each technique allows to collect the tracing message from many sources like BIOS, like ME, like ICH, and another integrated core. So okay.
Our talk is named Visa, but in fact Visa is only one component of whole hardware tracing chain. Visa, which means visualization of internal signals architecture, is actually a network of multiple multiplexers routing hardware signals from external hardware components to on-die logic analyzer. The main benefit of Visa is that you don't need to know a frequency on which operate selected signals. Visa operates by native clocks of chip and PCA of chips, and you only need to know a clock selector for a set of desired signals. This information can be get from a special file named Visa XML, which exists for every platform model and for every stepping. At this scheme, we depicted the fact that there are three types of multiplexers. Cilium, it is what is Visa actually. Cilium is central level multiplexer, is a top level multiplexer connected directly to ODLA. Ulium or unit level multiplexer receives signals from internal IP units and transmits them to one or more PLM. PLMs are chained together on multiple levels to finally route the selected signals to Cilium. Each multiplexer operates by lanes, each of 8 signals wide. At this scheme, we also depicted the fact that Visa can expose the chain of hardware signals to external logic analyzer. From TraceHub side, there is a special unit named Visa Register Controller. It defines an address range in TraceHub MIO for each of existing multiplexers. VRC also controls an access to multiplexers based on current security policy, which depends on current chip unlock mode. VRC also has so-called reply RAM, which can be used for automatic and fast reconfiguration of whole Visa network, triggered by some conditions. From security point of view, VRC is a basis for all Visa security. For example, there are some signals, such as data lines of some buses, which can transmit private data of software processes, operating systems, hardware blocks, and so they must be protected from sniffing by malicious actor. So VRC has designed with knowing of such critical signals and gives an access to such ULMs only if chip, SOC or PCH is currently unlocked by Intel or OEM engineer. Anyway, because of huge number of available signals, there can be errors in burn VRC configuration, so it can give access to some of sensitive signals. I have already mentioned it with the XML file. It's very important because it describes all of available multiplexers, their output lanes, and clocks. Also, it describes output groups of hardware signals for all which are allowed to trace. Also, it describes register addresses for controller registers of multiplexers. Without this information, it's practically impossible to reconstruct VISA network to capture some desired signals. Fortunately, we have found the VISA XML files for some platforms in Intel System Trace tool. We inspected all of available to public versions of System Studio and put together all the VISA XML files which we have found. It is what we have gathered. It's very interesting that for different versions of Intel System Studio, the VISA XML file for the same platform model and stepping can differ in sizes. We compared for changes to such files of the same chip and found that smaller version of VISA XML file contains less output groups of hardware signals. Also, we noted that both versions of VISA XML file contain identical declaration of multiplexers and their controller registers. So they differ only in a set of exposed hardware signals. We have found the fact to be very interesting. For each controller register, VISA XML file, along with the register address, defines some attribute named VISA standard. It's obvious that it defines type of control register, so it defines its content, its layout. Of course, Intel TraceHub IP library knows all of existing control registers and their types. So we have reverse engineered a part of Intel TraceHub library, and at this slide we depicted all standards for VISA registers, VISA control registers, which we have found. To use basic functionality of VISA network, only two types of control registers are needed. They are VISA lane, VISA lane, and VISA control. Some of standards which we have found, we have never seen in all of us VISA XML files. Let's consider VISA multiplexer more closely. Every multiplexer consists from a number of output lanes. Also, it has one or more input lanes associated with output lanes of other multiplexers from previous level, or with output group of hardware signals. Each input lane has selector starting from 1. And each input lane is tied with some clock. So for each output lane, the VISA lane register allows to select one input lane and specify its clock. CLM and PLMs use and select not native clocks of chips, but current clocks of lower level multiplexers. Now about ODLA, on-die logic analyzer. Different versions of trace hubs from various platforms contain ODLA with different parameters. For example, on-die logic analyzer from Broxton P Atom SoC is able to capture concurrently 10 output lanes of CLM or 80 signal lanes concurrently. On-die logic analyzer supports store-on-change compression, which greatly reduces traffic between trace hub and selected hardware interface. We have found that ODLA encodes digital data of signals in private format and sends them to global trace hub with master ID equal to 1. Trace decoder engine library has a special debug mode, after activating which you can expect the ODLA format, private format, and check correctness of trace decoder engine ODLA decoder. This ODLA decoder stores decoded data to a file named by default capture VCD decoder.vcd. It looks like depicted on slide. We have found that file is of poor, unusable format. Its timestamps in picoseconds and only binary data for VISA lanes is very annoying. In fact, you will need some transformations because you can use that file in a real work. At least we have written a special Python script displaying for signal lanes their values also in hex format. At this slide, we have placed trace decoder engine log for on-die logic analyzer. We specifically marked timestamp injection packet and native clock of detection condition by on-die logic analyzer. We decided to place on this slide all your steps you will need to do to start and decode trace data from hardware signals. Despite mentioning VISA XML file and one more NPK XML file, to do tracing of hardware signals, you also need a special file named interview.xml. It defines hardware events, associating them from signals of VISA XML file. On this slide, you can see the format of the file, and so you can write your own. Now about SOCHAP. SOCHAP is SOC chipset hardware architecture performance. It is a set of hardware counters, actually. It also uses VISA to access signal values, but instead of capturing them to digital data, it increments corresponding, it has a number of mask match registers pairs and can or increment corresponding counter or simple measure time duration during which some hardware event occurs. SOCHAP has native clocks SOCHAP operates on some clock to access signal values and increment counters. So we think it's obvious that ODLA, VISA, and SOCHAP are very powerful technologies. But do they have a real application for tasks such as hardware investigation, security investigations of hardware, of reverse engineering of hardware? Not just a hardware validation for which they are primarily designed. Yes, they have such application. Using ODLA and VISA, we have finally understood a thing called Intel on-chip system fabric. We were able in runtime see how IOSF works and confirmed and or rejected many of our suppositions. IOSF is a glue of all modern SOCs and PCHs, linking together various hardware. If you know how IOSF works, you have a key of all those doors and a system. You can control all hardware. So what is IOSF? IOSF is a private Intel on-die interconnect specification. Primarily designed for SOCs, by later extended to PCH. It allows Intel to seamlessly integrate third-party IP units and interchange the logics between various models and various models of the chips. We have found that IOSF specification defines 3 types of buses: primary, sideband, and FX. Also, IOSF specification defines a bridge to open core protocol bus with open specification. Also, it defines a number of bridges for legacy and external buses. For example, when PCI Express device issues some transaction, it goes a long way through IOSF segments, IOSF bridges, and finally arrives at system agent and memory controller. We also have found that each device in IOSF hierarchy has special unique identifier, named security attribute of initiator, or SAI. Using the SAI, the all-access control inside IOSF is performed. IOSF primary is developed for fast, for high speed primary communications or primary data flows. It replaces PCI Express for on-die communications and greatly extends its transaction layer specification. The heart of IOSF primary bus is a hardware unit named Primary Scalable Fabric, or PSF. It's a hub actually routing transaction between upstreams and downstream ports. It's very important that PSF supports point-to-point transaction between its devices, not going to mine CPU or system agent. Also, IOSF primary extending PCI Express supports different root spaces, allowing to isolate a group with independent address ranges These root spaces allow to isolate a group of devices from others. Also, IOSF primary bus supports different decode or routing modes. For example, PSF unit can select a target port or target device for a transaction based on its addresses, or a source of transaction can explicitly specify a target device by special identifier named destination ID. We have found that Intel Management Converged Security and Management Engine has a special bridge, very privileged bridge to IOSF primary bus, operating on destination IDs and issuing point-to-point transactions. Also, we have found that PSF allows to control VTD or IOMMU for devices connected to its ports. Now about IOSF sideband bus. It is a low-speed bus designed for all of out-of-band communications. For tasks as private configuration of devices, fuse distribution, or error reporting. It's really, if you have a full access to IOSF sideband bus, you can control the most part of a system. For example, you can interact with fuse controller and do many other very interesting things. Inside sideband bus, each device is globally identified by a so-called port ID. Also, for each operation, IOSF specification defines opcode. There are opcodes to read and write configuration of every device, to access its bars, and to access a private device configuration not accessible via standard PCI Express, PCI configuration header. We also found that Intel Management Engine has a bridge to IOSF sideband bus, very privileged. So Management Engine has full access to sideband bus and can control all hardware of PCH. Standard way to access IOSF sideband is via primary to sideband bridge, but it's very limited. In fact, you can access only limited number of devices and very limited its registers. If a chip, SoC or PCH currently is unlocked by Intel OEM engineer, you also have access to sideband via JTAG. At this slide, we have depicted, which we have found one of data sheets for Intel server chipsets. You can see all of three types of buses and devices connected to it, in devices connected to them, and how they interact. Also, the list of all available port IDs for all devices connected to IOSF sideband is unavailable in public. But we have such list for Intel server chipsets, and we'll show it to you as bonus in the end of our talk.
Okay, wake up. Now we will show the approach, the knowledge about IOSF to tracing the security issues data. It will be a key stored into special devices called Fuse controller on our platform. We will do it two ways, from ME and from sideband tracing through USF tracing. So I don't know, maybe it's 0 days, but Intel said nothing interesting about, because Intel didn't see our demos. So now we starting the capturing of buses.
We selected the path to the signals in the Visa XML file.
Yeah, you can see it here, that it is data signal into PCH chips, which we can capturing via Visa. And now we restarting ME because ME is reading the fuses only on start, only on after wake up, and we are stopping the tracing. After that, we download data from chip, and after that we have full trace. It's operation on this bus, and now we are reading information about fuses from ME
By JTAG.
by JTAG, yeah. And after you can see it's DD61, 9B, 7F, and many other. It's a really secret key, because on this key
it is a root for all other keys
it's
hierarchy.
root, on the basis of this key, encrypted and signed all file system, or internal file system of ME. And also you can see that we found these fuses in our tracing. And
They are much from JTAG and from Visa.
DD 61, 61, and other. So one moment. Okay. So now it is so the other components of Visa is software stack, but almost all utilities which you needed for debugging Intel CPU are included into Intel System Studio. So you can download the trial version of Intel System Studio from official website, and we are interested in the following components of System Studio. It's DAL and OpenAPC. We think it is different implementation of JTAG software stack, and system trace. It's packed with for supports for Visa supports. So we've found the such files into the directory. And these files with high entropy but some lines looks like equal. After that, we guessed that it is encrypted by CBC mode of some block ciphers. And of course, we found that it is true. The files encrypted by IS and ASCII, the DAL using output of PBKDF algorithm for fixed salt and password. And you can find salt and password in DLL for DAL. So we decrypted all files which we have. And we found interesting statistics. On this slide, you can see how to change the size of the DAL configuration directory, and interests the first line because you can see that the size is more than next. And this line, and the last lines. Also, we found many interesting in these decrypted files. We found a strange description for one of the fuses, some secret source, backend secret source bit, disable secret source or enable secret source. We don't know what it means, but it looks like strange. Also, we found that your hardware random number generator has deterministic mode, and it's of course for testing, and of course it works on microcode, on production microcode. If you read description.
You have no way to check whether on your platform it is enabled.
Unfortunately, yes, because the fuses program it in your CPU and you couldn't read it without any hardware vulnerability or microcode maybe. So the next part, the last part of our talk, it's topic about security. As Mark already said, Intel gives a few levels for unlocking of the market platforms, customers' platforms. The green, orange, red, and something else. It's green, it's public platform. It means that you haven't access to the security sensitive signals of Visa. You haven't access to JTAG core and ICH core, sideband, microcode, of course. It's only for market. And the second level, it's orange unlock. It means that it's unlocked for vendors, and you have access to reduced set of signals like ICH, GPO devices, and some other. And the next level, it's last level, the red, it's full access to debug capabilities. If you have red unlock, you can tracing any signals of Visa, you can get JTAG for IME, JTAG for CPU, JTAG for Encore devices, you can debugging microcode. It can use only Intel and people who download our proof of concept from GitHub. So we found also that we also found a Visa disable bit in configuration file for Fuse controller. And Intel can disable these technologies on customer platforms after manufacturing, but as we will see, for some reasons, it does not do it. How we will discuss the technique for getting orange and red unlock on the customer system. So the first and simple way it's vulnerability, and you can use vulnerability which we found. It's 00086. You can download proof of concept for gigabyte bricks from our GitHub. Also, we will publish the new version of proof of concept, which allows to bring up main CPU. Also, after that, you will get red unlock for this SOC. Also, we will show what it gives you as researchers. Now one moment. We will show you how to trace physical physical addresses of each memory transaction on this CPU.
It's very useful, for example, to debug
speculative execution, yeah.
Speculative execution bugs.
Out of order and many else. Okay, sorry. Okay. Now, what will be means this console is console for Visa. It's for downloading information.
For trace decoding.
Yeah, and output file is and its host and its target with RDP. It is Windows 10 and
read-write everything.
Reading this physical address. Also,
firstly, we start the code session.
We invalidate cache lines. We do invalidate cache lines. After that, we starting Visa, starting CPU, capturing data, downloading it from SOC, decoding data.
From a set of binary lanes, we form full address. In one column, timestamp of memory access, and in second, address of memory transaction.
And we found these physical addresses which pick by read-write everything. Okay. So okay. Of course, you can use another. You can try to another vulnerability for it. Intel had reported about a new portion of vulnerability in ME 2 weeks ago, and we think that you can use the vulnerability like that for finding 1 day for Visa unlocking. So we found also interesting behavior on TXE platform. We have already discussed problem with the manufacturing mode. It is another one. If you have platform working in manufacturing mode, this means with a high probability that your vendor's public key isn't set. It means you can generate public key, signature and unlock partition, special unlock partition. After that, you can get orange unlock for TXE core or ME core. And on TXE platforms, we found that this unlock gives access to MEGTAG. It is not true for desktop platforms, but we reported, and after that we reported about it in Intel, and Intel said that it is not problem, it is feature. I don't know. Okay, it's really funny because you haven't access to sideband, but you can get access to sideband
via management engine.
I don't know why it is not bug. So the next interesting technique, it is Intel JTAG password. We found that Encore devices for CPU has special JTAG registers for unlock in CPU and PCH. This register we found too. Also in another one configuration file we found some values which is very similar on JTAG password, like with funny comments make this 7 or 3 to enable another core. Yeah.
This fixed JTAG password is for all platforms.
We don't know it is true or not. It's a very older platform, but on another configuration file we found that CPU has fuse JTAG password select, and you can choose between static or dynamic passwords for JTAG. I remember you that if you have read unlock, you can use with your system anything. You can reading memory and you bypassing all protection technique without any problem. So we think this technique looks like this. You have manufacturing version of chips. You have some fuse station. You have Intel server, and on the factory, fuse station requests unique ID and password from server. Server generated new unique ID and password, save it into database. After that, it responds to fuse station this unique ID and password. Fuse station programming unique ID and hash from password into CPU or PCH. It's all on the factory. When you have trouble with your public platform, you need a special Intel engineer which can get unique ID from CPU or PCH. After that, he requests password from server. Server send password to engineer computer. After that, engineer computer can unlock CPU or PCH using password which received.
So if only one, the algorithm for JTAG password will be leaked, consequences are very bad.
It's really interesting, yeah. So we found also that it is not our fantasy. We found the presentation by Intel's engineer, which described unlock the CPU. After that, we found also this library, LEAP authorization, which has a special class for unlocking system and writing key into chipset or CPU. Also, on this slide, you can see the class interface for this library. So, I want to say that we didn't manage to get the JTAG password for our platform, but we think it's possible, and you can try to do it. So also the last way, it's hardware. For unlock, you need skip only one instruction.
It's from Intel Management Engine ROM.
Yeah. You can do it via, I don't know, fault injection or maybe another technique. After that, you get the unlock for your system. So, as results, we want to say that Visa is amazing technology for internal architecture research. You can tracing memory addresses, memory data. You can study speculative execution out of orders, internal buses. Also, we found that on public system has a special bits for disabling Visa and DFX, but on our platform it is not set. And also we found JTAG passwords, and we want to say it is not backdoor, it is only for debugging the market platform. Also, if you want to understand how does Intel CPU works, Dell configuration files, it is your choice, because these files contains many interesting information about internal kitchen. So, on this slide you can see our relative papers about JTAG, about DCI, about vulnerability which we found, and also about manufacturing mode. And so it's end. Thank you for your attention. Question, please.
Hi. So you showed at the beginning how you were sniffing the fuse data from the fuse controller. In what unlock mode was that possible?
It's possible only if you have a red unlock. Really, actually, for different signals, you have different access level. If you want, for example, to trace ICH core, you need orange unlock. And sometimes, if you have a green platform or without unlock, you can tracing small piece of signals. And I don't know, maybe it is help for your research without any unlock.
Thank you.
Thank you for a very good presentation. And I saw on the slide and in the demo, you guys extract a lot of different information from the fuses. And do you try actually classify this information? It's only the secret keys, or it's kind of like hash information for something?
You can find the details about what we instructed on our another presentation with Dmitry Sklarov about Intel Management Engine key genealogy. Really, it is base for key derivation. From these secrets, ME constructed all key, all vendors' key, like MFS key, like I don't know. Key for bootguard, yeah, and some part for PIVP.
That's actually very cool. I have a second question now. So you say a bootguard. How many security features broken based on this information, if you can extract it and can get it?
So I don't know the security feature which couldn't broken after that.
Okay, that's very cool. Thank you.
Okay, thank you.